Okay. Go ahead. Okay, so yeah, welcome back. So I want to go back into the discrete geometry of particle configurations. So the theorem I had was that if XE is a triangular graph plane. So it's again flipped. I think it's yeah.
Or this is very that was my first. I don't know, but it's just wait. Is he writing backwards? Why?
That's okay. So the plane. So something like this. So all the faces have to be triangles, but otherwise they can be like edges and very stuff sticking out. So and then we have this discrete Gauss-Bonnet theorem in the plane. So it says the following. So it's the sum over all points in X. So of the curvature is, so I want to write this in a fancy way. So it's the size of the lattice sphere times the Euler characteristic plus V times the perimeter minus the number of yeah, maybe zero without the so minus the number of boundary particles. So so this here is the perimeter, where we have to be a bit careful when we have something sticking out. So the perimeter should be taken in the sense of geometric measure theory. So as the inf of the length of the shortest smooth curve that surrounds the object. And so that means the wire edges need to be counted twice. So wire edges twice is the correct definition. And these are the boundary particles. So here all the particles sit on the boundary. So boundary particle is anything that touches the infinite face of R2 without the rest. Okay, so that's the boundary particles. And then that's the Euler characteristic here. So it's just number of vertices minus number of edges plus number of faces. So vertices, edges, and faces. So that's the Euler characteristic here, and there is okay. So now this is the size of the unit sphere in the graph metric. So the number of edges. So number edges of unit sphere in the triangular reference lattice, like here. So it happens to be 6 in the plane, but it's actually very useful not to call it 6, but to call it area of unit sphere in the lattice. So area in the sense of length. So d minus 1 dimensional Hausdorff matter. Okay, so then that's a very nice theorem, because it splits the curvature sum into a topological term and a sort of perimeter term. And so let's first maybe check on an example that this really works. So let's do an example. Okay, so and the curvature Okay, should I also maybe revise the curvature here? So the curvature is essentially the Euler curvature, but corrected by a boundary term. So I explained this yesterday. So it's the okay, so it's so yeah, so let's do let's recall the definition of the curvature. So it's in the interior of X, it's a little bit different from the boundary. So then it's just Euler curvature. So it's the difference between the size of the flat lattice sphere minus the size of the unit sphere around X. And then what you do when X is in the boundary, you're saying for a boundary particle it's somehow unfair to expect it to have such big a sphere around it. So you basically halve the reference here. So a half S1L minus S1 of X. Okay, so that's a sort of boundary corrected Euler curvature. So just this term is a very classical thing, was introduced by Euler for graphs. And so let's do an example to see that these definitions really make sense. So let's compute. Let's do maybe this example here. So let me start by doing the curvatures. So here all particles are boundary particles. So let's start with this guy. So its unit sphere has pretty few edges. It has only this one because this one is not there, 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 and this one is not there. So the unit sphere around this point has only one edge. But when you look for the reference here, so the k of x, it should be a half times 6, so it's 3 minus then this s1 of x here. So the size, so the number of edges here is really just 1. So actually notice that for these kind of irregular configurations, it is important that you define things in the right way, namely as lengths, as sort of areas of the sphere. So you shouldn't count points in the sphere. That would give you the wrong answer. And so this philosophy really comes from Ritchie curvature. So anybody who has ever heard of Ritchie curvature will know that Ritchie curvature measures how the length, how the area of the sphere as a function of radius differs from that in flat Euclidean space of the same dimension. So that is sort of measured by Ritchie. And so here we're doing the same thing. And in fact, so when you take a so-called discrete first order curvature, which I do here, which just compares the area, so it involves the sphere of radius 0 and the sphere of radius 1, then that's kind of the right definition. You can also go to second order curvatures and things like this when you compare a sphere of radius 1 and radius 2 or things like this. But in any case, so it's really, we measure the lengths here. So we get, for this point, we get the curvature 2. Then these three are kind of the same. So we get also 2. Now for this guy, the unit sphere around it has no edge. I mean, it still has a particle, but has no edge. So then we get 3 minus 0. So that happens to be 3. Okay, so this is the curvatures here. So we worked out the left-hand side. So then on the left-hand side, we get 2 plus 2 plus 2 plus 3 should be equal to. Let's check whether it's equal. So here the S1L is always 6 times. Okay, so what is the Euler characteristic of this thing? So we need to count vertices minus edges plus faces. So vertices, there happen to be 4 of them here, yeah. So edges, I also have 4. And faces, I have just 1. It's this thing here is a face. Okay, so 4 minus 4 plus 1. Okay, and so now plus 3 times what? So what's the perimeter of this thing? Well, okay, so the perimeter, I need to take a contour around the whole thing. So and that tells me to, yeah, and so that counts this edge somehow twice, yeah, because if I shrink the contour, I count it twice. So the perimeter here gives me so it's 1, 2, 3, 4, 5. Okay. And how many boundary particles do I have? Well, there's all particles sit on the boundary here to cut out the boring parts in the interior where nothing happens. So we have 5 minus 4. Okay, so now this stuff here is sort of 6 plus 3, and so this gives 9, and on the left we have 2 plus 2 plus 2 plus 3 is also 9. So that's an example how this works. So in this discrete Gauss-Bonnet, and notice that so I'm focusing in this example really on what happens on the boundary to explain the boundary correction. And so we're going to do a proper class for the second part. So I give you the fun part because we do it on a sphere with boundary-less configurations. Yeah, so that's a lot of fun. So then if you have so this Gauss-Bonnet also works on manifolds just fine. So it's nicest in the case when the faces completely tile the manifold. Yeah, so then you have a triangulation of the manifold, and then you can so it's going to be your job to check the Gauss-Bonnet on the sphere for actually just to connect to the previous lecture. I didn't use any octahedra, but we're going to have an icosahedron and a tetrahedron. So you're going to check Gauss-Bonnet for that. So so that's how it works, and and here the message really is, if you define this boundary correction kind of right, then this works for general configurations. So that's something that is kind of our achievement here with my co-worker, Lucia De Luca, that we really worked out this formula for general, possibly very nasty configurations. And without this term on compact manifolds is a result by Oliver. So Oliver Knill wrote a nice paper, but I'm not sure he was the first to observe it in the manifold case, because it's somehow implicit in proofs of well, I mean, in cohomology theories when you use a singular complex. So what he worked out is really versions of this also in the plane, but for nice configurations. Okay, so he worked out this prefactor, and so we added the corrections. Okay, so now let's maybe do the proof of this. I think it's quite nice to really do the proof. So it's not difficult to prove this thing. So I want to explain the proof. So yeah, maybe go for the proof here. So what we're gonna do is that there's some so if we have a triangular graph in a plane, so triangular means all faces are triangles, and so that gives us some nice properties. So we define so we introduce some local quantities which are a little more so introduce sort of local quantities. So So the whole point of this argument is really to localize this Euler characteristic. Yeah. So it's really the discrete sum over some local quantities. Yeah. So I mean, in topology, you often work directly with global quantities, and you don't care what happens locally. But when you do cohomology theory, you often write topological invariants as integrals over some characteristic classes. Yeah. So those of you who know topology may have heard of that. Yeah. Okay. So there's usually objects that generate the cohomology groups, and you integrate over them. And here this curvature generates the Euler characteristic. But it's a local quantity because it's defined only with local information. Yeah. So it's a fantastic example of a local to global kind of result. So we introduce local quantities. So a boring one. I apologize. So V naught of x is equal to 1. So yeah, I just need it. It so happens. Then V1 of x is the length of the unit sphere, I mean number of edges, and so V0 of x is so to speak the just the number of I don't know, it's just one. Maybe so I don't want to over-theorize. I could if you ask me nicely over coffee. Okay, and then so the V2 of x we also need, so it's the number of faces in the ball of radius 1 of x. Okay, so basically this is a 0-dimensional thing, that's a 1-dimensional thing, that's a 2-dimensional thing. So these are sort of local quantities. And so then you have some properties. So I found the nice terminology in Knill's paper, so he calls them handshake. So a nice terminology of Harvard. So we call it handshake. So it's basically when you have these kind of configurations. So first of all, so if you sum over all x in x, the V0 of x, so this capital V0 of x, you get back the little V0, which is the number of vertices. Okay, because so that's a kind of trivial relation because we set the V0 of x equal to 1. Then if we sum over the V1 of x, so what do we get? Well, maybe draw a little here of adjacent triangles. So for example, this edge here, so whatever edge you have, it belongs to two spheres. Yeah. It's an interior edge, so it belongs to two spheres, not more nor less. So the rough answer is 2 times V1, but that's not quite true because if you have a boundary edge, so for example, let's do this edge here. It only belongs to one sphere, but that's a boundary edge. So I should subtract basically minus the so I should subtract so minus the number of regular boundary edges. So like these gray guys, and then I also could have a kind of wire edge, which is a nastier guy like here. So this would be a regular boundary edge. Then I've overcounted by 1. But if I have a wire edge, I have overcounted by 2. Okay. So I need to subtract these guys twice. So this things I called outer wire edges. So and we see that so by this simple definition here, trying to count the edges like this, we get actually another way of defining this perimeter, which I introduced. We see it's right, so it's exactly 2v1 minus the perimeter. Yeah. So this handshake stuff matches super nicely with sort of perimeters. And then let's also do the third handshake thing. So we won't need it, but I want to show it. So the sum over x and x. Okay, no, maybe we will need it. So so of v2 of x, so the number of faces. So now if you have a triangular graph, so in a triangular graph, take any face. So there's no regularity requirement. So each face has exactly 3 corners because it's triangle. So therefore, when you sum this, you overcount each face by a factor 3. Okay, because each face has 3 vertices, so it belongs to 3 spheres. Yeah, the only sphere to which a face belongs is when the only balls to which a face belongs is the ball of radius 1 around its own edges. Yeah, and so therefore here you overcount by 3. So it's basically 3 times the number of faces. Okay, so in a triangular graph, this works out nice. And but note that's exactly this correct counting of the perimeter of the configurations that I get here. And so now armed with this, it's now pretty elementary calculation to get a Gauss-Bonnet. So let's kind of do it. Can you still see this? Yeah, I'm not sure. Yeah, the green lines help that you draw. So let's see what I'm writing. So let's start backwards. So the Euler characteristic. So that's this. So it's sum k equals 0 to 2. So it's basically k equals 0 to 2, and then it's minus 1 to the k times the vk. Okay, so the total number, and then so the next thing we use is we use this handshake stuff. Okay, so handshake. So we can write this as sum k equals 0 to 2 minus 1 to the k, and then we just sum x in x. So it's the vk of x divided by k plus 1, and then but for the edges. So for the second one here, we let's solve this for v1. So v1 is basically a half sum x, v1 of x, but we get plus p of x. Okay, so we get an extra term with also in the half. Okay, so when we solve the second handshake for the number of edges, we get an extra term of a half the perimeter. But here, because it's because there is a minus sign in front of the v1, so we get here minus a half times p of x. That's by handshake. So now, but this thing here. So the number of so I explained to you yesterday that this thing here is exactly okay. So I think I don't want to. Okay, so maybe let's do it even slower. So change the order of the sum. So we take the sum inside from the handshake, so from the Euler characteristic. So and then we get sum k equals 0 to 2 minus 1 to the k vk of x over k plus 1. So here we have the minus a half p of x. I keep it out. Okay, and so now then this thing here is just the.
You see my eye? My concept? That's right.
Whatever CMI means, it's not us. Okay, so now this thing is exactly the Euler curvature. So this is exactly 1/6 of the so it's exactly this term here. So the one from the V0 gives me this term, and the other two terms conspire. So it's 1/6 times the Euler curvature, which I discussed yesterday. So that's really the Euler curvature that sits right here, and so now I have to be a little bit careful because the correct curvature has a different term when you have a boundary particle. So there is a correction coming from boundary particles. So let's distinguish this. So it's basically 1/6 k of x if x is in the interior, and it's not that when it's on the boundary. So if so it's 1/6 of k of x and in the interior, and it's basically 1/6 k of x. So we have so then we get so when we were on the boundary, so we count it differently because the first term so this was so we have an extra term here which is a 3, so which is so it's a 3/6. So if x is a boundary particle, okay. So because there I subtracted here, so I've so the correct curvature has only half the sphere here. So I'd have to add the extra 3. And so now I get sort of nice term. So it's basically so the sum over x in x of I get k of x over 6 plus sum x in delta x. So I write it with 3 over 6, and then minus a half the perimeter of x, and then just sort it out. So it's basically and so this term is really plus a half times the number of boundary particles. Okay, now you multiply by 6 and you're done. Okay, so that's basically the proof. So here we go. So that's the Gaussian proof. I think it's a very nice sort of discrete integration, so to speak, where at the end you find a topological. So now the other thing is quite similar, but I think for completeness, I also want to show how to prove the so we have this geometric energy decomposition. So let's look at this other theorem. So this was geometric energy. Decomposition. Yeah, maybe not with the energy, but let's say the geometric decomposition of the number of edges. So the number of edges are the same as in the discrete Heitmann-Radon model, the energy. So minus the number of edges is minus Vn plus P of x plus the defect measure mu of x plus 3 times Euler characteristic of x. And so in this case, E was the bond graph. So it could have like pentagons or some other thing. 5 here, that's a nice pentagon. And then maybe so something like this. And then we basically triangulated the bond graph. So where we basically added extra edges if we have pentagons or whatever. So then we have this E bar minus E is basically the number of quadrilaterals plus twice the number of pentagons plus dot dot dot. So whenever we have a face that is not a triangle in the original bond graph, we get a penalty. And so this thing we call the defect measure. So that's that. And then I think the other two terms were already explained. So then let's prove this one. So the proof is quite similar, and I think it's also nice to convince yourself this is correct. So again we can decompose that. So it's basically minus the number of edges is the same as minus the number of edges in the triangulated graph plus mu of x. So this is basically just the definition of the defect measure, like this. So defects are faces that are not triangles in my picture here. And then the next thing is I can, so the total number of edges, which is the same as my V1 in the notation above, so the total number of edges of the regular graph. And so now I use the handshake again. So so let me bring this up here. So we worked out by handshake. So the V1 is basically this quantity here. So it's just the local size of the unit sphere at x summed over x plus a global quantity, which is the perimeter. So we do the so this is again the handshake. So we get minus a half. So sum over x v1 of x plus the perimeter p of x plus the defect measure mu of x. Okay, and so now push it up. Yeah. Okay, so that's maybe I push it up even more. Okay, so we have this by the handshake, and so then but this we can again trade for the Euler curvature. So it's basically So so it's let's say so now let's bring in this this Euler curvature. So it was basically so it's basically 6 minus v1 of x. Okay, so it's 6 minus v1 of x. So if we solve for v1 of x, it's basically minus a half. Yeah, let's maybe solve here. So then the v1 of x is 6 minus Euler of x. Okay, so so we get minus a half 6 minus the Euler curvature of x. So I want to write it like this first, plus mu of x. Okay, so this is here definition of the Euler curvature, and so now we can clean stuff here. Okay, so I forgot to write the sum over x. So that gives me already a nice term in front. So it's minus a 3n in front. So minus 6 halves, so minus 3n in front from the constant term. Then I get plus a half okay, so I noticed I forgot to copy the term here with the perimeter, so it's still there, minus a half x. So that term sits still here. So it's so now I get a plus 1/2 sum x in x, the Euler curvature of x minus a half p of x plus the defect measure. So that looks quite nice. So now now let's be a little more careful now with the so now we want to pass to the corrected Euler curvature, corrected by boundary terms. So, and I want to resplit somehow this into -3 times the number of interior particles. So minus, but only -3/2 the number of boundary particles. And then we can substitute, so then we can substitute here the corrected curvature. So sum x and x. So this is the boundary corrected Euler is sitting here, and then these two terms stay minus a half p of x plus mu of x. So so and now I can use the Gauss-Bonnet. So that's now my secret weapon. So so now I have the Gauss-Bonnet. I can use it precisely here. So this is 3. So by Gauss-Bonnet, this is 3 times the Euler characteristic. So plus 3/2 p of x minus the number of boundary particles. Okay, so that's the Gauss-Bonnet. And now this correction that I had here with the number of boundary particles, something beautiful happens because that drops. So it bothered me in the Gauss-Bonnet because it was kind of an annoying term, but that term exactly cancels this term, which came from the definition of the modified Euler curvature. So, and then to clean things up, so I really get minus 3 times the number of particles plus perimeter plus defect measure plus 3 times Euler characteristic. Okay, so that's it. So in particular, in the final result, what is particularly nice is that all these contributions that I had to introduce from, triangulating the original bond graph, they're gone, because the defect measure is just defined in terms of the original graph, number of quadrilaterals plus twice number of pentagons plus 3 times number of hexagons plus 4 times number of heptagons. So it's an intrinsic quantity of the original graph. The perimeter, just when the edges have all length 1, it's the inf of the curve lengths of the shortest smooth curve around it, and the Euler characteristic is the Euler characteristic. So all the nasty terms are finally gone, and we get a nice energy decomposition. And so remember that we call sort of minus this is the Heitmann-Radon energy of this endpoint configuration. Where the Heitmann-Radon is, I took this very narrow and whatever Jones type potential, which has a potential where we are at -1, sitting at 1. So it's sum 1 less or equal I less than j less or equal n. So the V Heitmann-Radon of xi minus xj. And the Heitmann-Radon was the lim as r goes to, as p goes to infinity of r to the minus 2p minus 2r to the minus p. So that's okay. So it's just this very stiff and brittle Lennard-Jones, and so basically the quantity I've computed here is exactly this combinatorial part of the energy. And so now we split it nicely into different terms, and so I think I already explained a little bit yesterday. So these different terms, they all do something. So for example, the Euler characteristic here in the plane is so it happens to be the number of connected components. So for example, if you have a configuration that is disconnected, that has 2 connected components, what the energy wants is to slide them towards each other to touch. So lowers the Euler characteristic. So the defect measure says you want the interior faces all to be triangles. That's good. The quadrilaterals are bad. Triangles are good. And the perimeter says, well, you don't want a random kind of messy shape with stuff sticking out, but at the end, so for nice particle numbers, you're going to see in the class that the optimizer for this Heitmann-Radon will be a thing called the wolf shape of this system. So it's kind of a regular hexagon. Yeah. So this perimeter, it kind of drives the shape. This drives the lack of defects, and this drives the fact that the thing wants to be connected. And so this is an invariant term that we subtracted out, because that's a kind of -1 for each bond coming from the depths of this potential wave.
Excuse me.
Yeah.
In the original Heitmann-Radon formula, you don't get this classification.
No. There's no splitting. I mean, they just write the energy like this. So the splitting is really us.
Yeah.
So,
5 minutes. Yeah, 5 minutes.
Yeah. I mean, I can do it in even less. Okay, so I basically explained what I wanted to explain, and then we can move to the class. So so that was a question.
To what extent is having this Lennard-Jones? So it's more how applicable is it?
Okay, so maybe what I should do is pull my because it's interesting. So because I of course when we did this work, we asked ourselves the same question, how far is the Lennard-Jones? So one of my questions on the sheet is actually about that. So let me take out this problem sheets already, so we can work on them later if we want. Yeah, at least show you the sheet. So I have, maybe talk you through this. So here's a Lennard-Jones question for the sheet. So that's on how applicable that is to the Lennard-Jones. So yeah, the stuff that's written, I mean, I happy to pass on these things, so you can read this, but I want to maybe explain this pictures here. So yeah, can we pass this? I'm just pass this along or pass on this side. So yeah, with that, that's something in the back. So hi, Danilo, glad to see you. So I'm Gero Friesecke. Yeah. So this so here so in the Lennard-Jones there is a softness parameter, and so that's the P in the Lennard-Jones, and so here I'm comparing things. So there is so here I put a sort of defect here. So that's this configuration, and this is a crystalline. So that's a subset of the lattice, and this Heitmann radian is a good approximation when the P is large. So for example, P equals 10 gives, so then the Heitmann radian gives a pretty good prediction. For P equals 6, it also gives the right prediction, namely that this non-symmetric configuration here, so yeah, that's not symmetric. So the outer guys don't sit at equal distance. So if you want, in physics terms, there's a symmetry breaking that has happened. So when you soften the potential, you get a symmetry breaking, but you get a regularity of the faces because they become triangles. And so this happens for P equals large, for large P, and in fact for the standard Lennard-Jones with 6, again this triangular lattice configuration wins. When you make the potential very soft, it's the other way around. So in the Lennard-Jones world, so the analogon what's for you, Ed, is kind of the curvature. So here it's sort of driven by the softness of the potential. If you make this soft, then the defect wins, because if you look carefully here, so the red curve is kind of below. So you need to do some bond length relaxation of these configurations to get meaningful trial configurations, because here the bond lengths are too, so here the bond lengths are too long. If you're keeping particles at distance r from the origin and take equal angles 2 pi over 5, then these bond lengths are going to be bigger than r. Yeah, I don't care. Unlike Doug, I don't care exactly how much they're bigger, but they're bigger. Okay, so that's your tan from yesterday. Okay, so but they're bigger, so therefore the whole configuration will relax. So the minimum configuration is at sort of 0.94 instead of 1, and so then this guy will win. So for the soft potentials, the Heitmann radian is not a good prediction, because these defects are favored for the. But I think the energy decomposition is still useful, because you can now nicely see the competition here between, yeah, I don't want to tell you which 2 of the 6 terms drive it, but I think, yeah, Ed probably knows it's elastic energy versus perimeter. Right? You have fewer boundary edges, but you pay with elastic energy.
So is that, if you would change the constant Q instead of the power, does that also kind of shift whether the triangular and the pentagon?
Okay, so
just the softness of the
okay, so I'm very proud of figuring out. So it's not my main contribution to science, but one contribution I'm proud of in this Lennard-Jones mess is exactly not doing this, because what I think should be kept constant is the depth of the potential web. So it's the cost of debonding one particle, because that's when you do really simulations or something like this. I mean, if particle is far apart, it feels 0 potential, and by attaching it gains -1. So this normalization with the Leonard Jones, which the way I wrote it here with the 2p minus yeah, where did I yeah, I think I wrote it here. So so with the r to the minus 2p minus 2r to the minus p, I think it's a neat way of normalizing, because you normalize the interparticle favor distance to 1 and the depth of the potential where to minus 1. But of course you can. So if you do what you suggest, it's perfectly legitimate to do it. You know, you can.
Maybe it's a silly question, but does it change the triangular? I mean, yeah, portion of the pentagon.
Okay, so you can okay, so by renormalizing it's equivalent to here.
Okay.
So it's really equivalent. So when you scale, so when you change the constant 2, you then do an overall rescaling of the distances and of the energy scale, because you can choose both the distance scale and the energy scale, and then after renormalizing the length scale and the energy scale, it's equivalent to this. So it doesn't give you anything new. So it's perfectly fine. And I mean, there may be reasons in other potential where this 2 kind of varies, but I think it's nice to normalize the potential for the fast icon. Okay, yeah. So here we go. That's what I wanted to say, and definitely I don't want to stand in the way of coffee. That's the biggest crime of any lecture, all right? So and then after that, I want you to work on this sheet thing. So, okay. And then we discuss it at the end.
For preparing a very nice sheets. Okay. Time for coffee, and then we come back and we start solving things.
So yeah, before we go to the class stuff, and I talk a little more about the problems I put up. I did want to explain some point, mainly this continuous Gauss-Bonnet. So one thing you can do. So we had this discrete Gauss-Bonnet. So we had basically some x in x of k of x was basically the unit length in the reference lattice times the Euler characteristic plus some correction minus sharp boundary. And so this was the discrete case. And so let's do at least the continuous thing in the plane. So continuous in the plane. So what you do in the plane. So when you have a sort of polygonal domain, let's say any sort of polygon, whatever. So there is a way also of defining the boundary curvature. And it's done as follows. So there are 2 cases, like a kind of flat case or non-flat case. And so in a continuous case, you do a boundary curvature as follows. So that's basically like this Ritchie idea, but applied to the boundary. So I want to mention this. So K. So it's a sort of the boundary is basically you take for a boundary point like x, or here another boundary point x, you take a small sphere of radius r, okay, and then you compare the length of the sphere intersect with the domain, sort of the domain omega here. So you take half the reference sphere, but in the Euclidean space, so not in the lattice, but in the continuous space, times, and so you subtract the lim as r goes to 0. So that's the length of SR Euclidean of x intersect omega, and you divide by r. so this for x in the boundary. Okay, so this works also for like a curved boundary or whatever. And then, but sort of for polygon, it would be something like this. And so then what this gives you is exactly this. So it's basically in this case the half sphere has length pi, and then it's pi minus alpha. So this is what this gives you. So a half the Euclidean length is really this pi here. And so for polygon, so when you do the Gauss-Bonnet in the plane, so one way of doing this in the plane would be so in the continuous you have the integral over omega. So you take the Gauss curvature plus integral delta omega this car boundary against the arc length, and so this in this case it gives the S1 in the Euclidean space times the Euler characteristic of omega. So for this set I've drawn here, it would be just 1, but this thing here is a 2 pi. So I'm just saying the 6 that showed up in my discrete Gauss-Bonnet is the 2 pi of the continuous guys. Okay, so the 6 is really the discretization of 2 pi. So I think that's an important conceptual insight. So that's why I didn't want to write the 6 here, but the number of edges in the lattice sphere. So that's what replaces the 2 pi in the discrete world. So that's the canonical thing. So the number of edges in the unit sphere in the graph metric. Yeah, so each edge is length 1 in the graph metric. You take the Euclidean metric and discuss the 2 pi. And so I mean, yeah, so it's just to explain this. Now, if you go in a curved surface, so here this would be, so in the plane, this would be 0. But if you take a geodesic polygon on a curved surface, then this formula is still correct. Okay. So that's sort of the story I wanted to explain. So it's just to explain where the 6 coming from and where there's the 2 pi in the usual thing. So for example, for a manifold, so if you have a closed 2D manifold, so this is Gauss-Bonnet, and so for closed 2-dimensional manifold, you have integral m of the Gauss curvature is just 2 pi Euler characteristic. Okay, so that's how these formula are connected. Okay, so yeah, here we go. So now what I wanted to do is get you to work on the sheet and maybe talk a little more. So I have like 3 different kinds of problems. So depending on what you're interested in, therefore 3 different kinds of people. So I think the first one is really core for what I was explaining because it goes into this discrete configurations. So I'm asking you to sort of redo the Gauss-Bonnet on the sphere by taking some standard triangulations with constant curvature. So the constant discrete curvature triangulations, there are not that many of them. Take the tetrahedron or the icosahedron. Yeah, so that's a triangulation of the sphere which has constant discrete curvature. Okay, and then so I just want you to work out what this curvature is and correctly sum them up, and hopefully you get this. And if you happen to know that the Euler characteristic of S2 is 2, this confirms what you already know. If you don't know the Euler characteristic of the sphere, it's one way of working it out, assuming the Gauss-Bonnet theorem. And then there's a second point here. So it's sometimes okay. So we heard already in the tutorials like this morning, and Alexander's very nice tutorial. We heard how to verify that something is optimal, but it's also sometimes nice to verify that something is not optimal. And so here, so that gives you a very simple proof of the existence of defects with Gauss-Bonnet. But I want you to think about it. It's really elementary. You don't need to think very hard, but you need to show that for each triangulation of the sphere, there exists a defect. So how are you going to do that? Well, that's the first question. I think everybody should be able to do that. Then the second thing is I want you to check this geometric energy decomposition for the Heitman radian. In this example I've drawn, so that's actually drawn by computer, so all the edges have one length 1. So that's a perfectly fine configuration for the Heitman radian. But just if you work out these different contributions, you should confirm the decomposition. And then the last part in question 1 is really looking a bit at the validity of this Heitman radian limit or not, depending on soft versus hard potentials. So that goes a little more into, so that's really a phase transition between defect and not defect driven by softness or potential. We talked about this before the break. So I think this is fun. And also I want you to explain as much as you can about these graphs from the theory and the decomposition. So for example, can you explain the minimum value of the Lennard-Jones, of the blue Lennard-Jones here? You know, it's about -9, but why is it -9? Can you explain this? So here we go. So that's for people who really want to look at these discrete configurations. Then I have another question. So that's for people coming more from like stochastics or differential equations. So it's like, I call it a hiker's guide for approach to equilibrium for Langevin dynamics. So yesterday I showed you simulation of Langevin dynamics where we really saw particles crystallizing in the plane. So this is really physical dynamics for the 612 Lennard-Jones modeling a gas at low temperature. So it's not a Coulomb gas. The real gases are not Coulomb gases. They are Lennard-Jones gases. So because the atoms attract at long range and repel at short range. Okay, and so for this Langevin equation, we notice that we need to go to long time and low temperatures to see the crystallization. But here it makes you check that the free energy is really the Lyapunov function, and also it makes you check another thing, namely that the Gibbs measure, where I showed you it's the minimizer of free energy. I did not show it's the unique equilibrium of the dynamics. So for people who come from gradient descent dynamics, it's nothing new, but the Langevin equation is not the gradient flow of the free energy. Okay, so a priori it could have other equilibria. So because there could be regions where the free energy maybe stays constant in time or whatever. So it's really checking that for the Langevin dynamics, the Gibbs measure is the unique equilibrium. Okay, and so yeah, so that's for people who know a bit of stochastics and or partial differential equations and like to integrate by parts and stuff like this. So I think this stuff is very hard to find in the literature. So I call it a hiker's guide because I don't know another hiker's guide to this. So because it's quite a intricate equation because of the damping and the noise. And then the third thing is for people who like splitting things into bulk and surface or whatever. So that's again going back to the Heitman radian model. So there are special kind of configurations that are regular hexagons. So for particular magic particle numbers, so a regular hexagon is a good candidate for a minimizer, and it shows you an alternative proof of how to showing that that's a minimizer by viewing this particle configuration as so we could think of this as a Voronoi cell type picture. So as a sort of continuum. So make it into a continuum set by attaching a little hexagon around each particle so that these things match. And then define a surface energy and use the n-isotropic version of the isoperimetric inequality. So in 2 dimensions, we all know that if you want to minimize area for given volume of a shape, you get the circle. And similarly for n-isotropic surface energies which are integrating some function that depends on the normal, so it depends on the direction of the surface. Then you get also a unique minimizer called the Wolf shape. So that's a sort of isoperimetric inequality. So for anisotropic sets. And so that can be used. So these are known theorems, so to speak, can be used to show that this thing is actually optimal for magic, for these magic particle numbers. And then there's a little teaser for something I do maybe on Friday. So for Outlook, so which of these things do you think minimizes the Heitmann-Radon energy? So I've drawn 3 different shapes. They all look reasonable. They are crystalline configurations, but which of them is best? So which of them is? So that's a more difficult question. Okay, so yeah, so here we go. So in discrete geometry, I think it's pretty easy to do. The Langevin dynamics is kind of hard work because you need to integrate by parts a lot and collect terms. But if you do it right, it comes out right. And the last one is sort of talking about a continuum picture of these configurations, which gives you an exact result in this case. So here we go. I think I let you work, and we do it like this. So if yeah, maybe it's more fun if you form small groups or something like this, or at least this 2 of you, and then at the end we can maybe sum up. So ideally, different people are interested in different questions, and we can sum up.
So thank you.